Okay, so in this lecture I am going to be talking about the RC circuit natural response using the Laplace transform. So objective number one is to use the L transform to get the time response of the capacitor voltage and current without initial conditions. Then next I am going to use the L transform to get the time response of the capacitor voltage and current with initial conditions. Then number three, I'm going to derive the power of the capacitor expression in the time domain. And then number four, I am going to derive the energy of the capacitor expression in the time domain. So to start with the circuit without initial condition. So I have my resistor here and a capacitor here. The initial condition is set to 0. So there is no voltage across the terminals of this capacitor. So the representation of elements in the S domain. So R is just goes from the time domain to the S domain as R. And ZC of S is represented as 1 over SC. Now I put ZC of S there because there is no impedance of a capacitor in the time domain. It only exists in the S domain. So ZC of S is going to be 1 over SC. That's the impedance of a capacitor. So next I'm going to assign current directions. In my schematic here, the current directions that I'm going to be using in this schematic is this orientation, just completely clockwise. And so that's my current directions. And so now I'm going to begin to look for the voltage. So current distribution at VC. VC is that node up here. Okay, so at VC, what do I have? I have IR of S equals IC of S. Then that expands into 0 minus VC of S divided by R equals VC of S divided by 1 over SC. Then the next step is to have negative VC of S divided by R equals SC VC of S. Next I have 0 equals SC VC of S plus VC of S divided by R. Continuing here to get voltage, now I have 0 equals VC of S times SC plus 1 over R. Then VC of S, as you can see, is now 0 because anything, when you transfer SC plus 1 over R to the left side, 0 over that is going to give you 0. So VC of S is going to be equal to 0. And so going into the time domain, going from the S domain to the time domain, that translation or that transform is going to arrive you at VC of T equals 0. This makes sense because without an initial condition, the VC of T should be 0. The voltage of the capacitor with time, that is, should be 0. So that makes good intuitive sense. So with the current, IC of T equals C dVC of T dt, which equals C d of 0 dt, which of course equals 0. Okay, so that makes sense too because you're going to expect that if your voltage is 0, then your current should be 0 as well. So that all makes good intuitive sense. So I'm going to look at a voltage plot now. Voltage plot is just this. Okay, so it's 0 and it's across 5 time constants. 5 times R times C in this particular circuit gives me 50 milliseconds for my time span that I want to plot this over. Okay, so I plotted it for 5 time constants. And so as you can see, it's a horizontal line, 0, all the way through. So that's my voltage plot. And then my current plot looks like this. Again, that's 0 all the way through across my span of a time range. Okay, so that is that. Now, next, the circuit with initial condition. That circuit is same thing except for I'm putting an initial condition of 5 volts over the capacitor. So with that being the case, now I have a little bit of a different S-domain representation. It's only different in the fact that I'm going to be adding something to it now. So R is still R, Z, C of S is still 1 over SC, and now I have this other element, VC of T sub 0 equals VC of T sub 0 divided by S. VC of T sub 0 is the voltage of the capacitor at time 0. Before that was simply, without an initial condition, VC of T sub 0 was equal to 0, and 0 over S is going to give you 0, so therefore you just discount it and you don't even include it into what you're doing. But now that it actually has a value of 5 volts, you're going to include it into that because now you have that initial condition. Now, assigning current directions. So I assign my current direction like this. I kept it the same. I kept it as clockwise. And so this is my circuit setup here, my circuit schematic. And VC of T sub 0 divided by S is here with this orientation. Okay, so note VC is the whole assembly of the passive element plus the initial condition element. Okay, so it's all of this, including that initial condition element there. All right, so next let's go derive the voltage of this. So the current distribution at VC, again, VC is here at the top, and I'm going to look at the current distribution there. So as before, IR of S equals IC of S, and then IR of S decomposes into 0 minus VC of S divided by R. That's equal to the decomposition of IC of S, which is now VC of S minus VC of T sub 0 divided by S minus 0 divided by 1 over SC. Then next that becomes negative VC of S divided by R equals SC VC of S minus C VC of T sub 0. Then I have negative SC VC of S minus VC of S divided by R equals negative C VC of T sub 0. Then next I have SC VC of S plus VC of S over R equals C VC of T sub 0. Then next I have VC of S times SC plus 1 over R equals C VC of T sub 0. Then I have VC of S times RCS plus 1 divided by R equals C VC of T sub 0. Then I have VC of S equals RC VC of T sub 0 divided by RCS plus 1. Then when I put that into standardized form, then I have VC of S equals VC of T sub 0 divided by S plus 1 over RC. Then the transform of that into the time domain becomes VC of T equals VC of T sub 0 times e to the negative t divided by RC. So in any circuits book that you look into that covers the Laplace transform, it'll also have a table of Laplace transform relations between the S domain and the T domain, and that is where I'm getting this expression from for VC of T. Now the voltage plot, well, what does that look like? Well, it starts off at 5, and then over that time span, over those 5 time constants, by the time it gets to 50 milliseconds in this particular example with the values that I'm using, then basically it goes down to 0. So that all makes intuitive sense, especially when you look at the equation there. VC of T sub 0 times e to the negative t over RC. That all makes intuitive sense. Okay, what about the current? Well, current distribution at VC, at that node, at that top node, okay? So IC of S equals IR of S as before. and then IC of S equals 0 minus VC of S divided by R, and then you have IC of S equals negative VC of S divided by R. Now I'm going to use the function for voltage to get the current. And so IC of S equals negative 1 over R times VC of T sub 0 divided by S plus 1 over RC. Remember, that is my expression for voltage. Briefly go back to that, and you can see my expression for voltage in the S domain, VC of T sub 0 divided by S plus 1 over RC. Go back to where we were, and so that's where I put it. I put it right there. So now next, IC of S is equal to negative VC of T sub 0 divided by R times 1 over S plus RC, or 1 over S plus 1 over RC. Now IC of S is negative, so it means that it is opposite in direction to the schematic and is coming out of the positive terminal on the schematic. With the correction on the schematic, this becomes IC of S equals VC of T sub 0 divided by R times 1 over S plus 1 over RC. Okay, and then that translates into IC of T equals VC of T sub 0 divided by R times e to the negative t divided by RC. And so current derivation, what if you do not have the voltage function to use for deriving current? So let's just say you don't start with the voltage. Let's say you have no voltage function in order to put into your IC of S relationship there. Then, can you get that all by itself? So can you derive the current independently? Yes, this is what I'll show next. So the current derivation, voltage distribution around the loop. So VR of S plus VC of T sub 0 divided by S plus IC of S times ZC of S equals 0. Okay, so it's around your loop, and this is the loop equation, or your mesh that you have. This is your equation that comes from going around that loop or going around that mesh and seeing what you have there for voltage distribution around that loop, which is actually still a mesh in this case. Okay, so IR of S times R plus VC of T sub 0 divided by S equals negative IC of S times ZC of S. Now that's going to be my equation number 1. Note, IR of S is equal to IC of S. Now that's going to be an equation number 2, because I want to basically put IRS in terms that get me a step closer to getting IC of S, and right here it's directly exactly equal to it. So therefore I'm just going to put equation 2 into equation 1. And so when I do that, now I have IC of S times R plus VC of T sub 0 divided by S equals negative IC of S times ZC of S. And as you know, ZC of S is 1 over SC. So now I have IC of S times R plus VC of T sub 0 divided by S equals negative IC of S times 1 over SC. And so now I have VC of T sub 0 divided by S equals negative IC of S times 1 over SC minus IC of S times R. Now I have VC of T sub 0 divided by S equals negative IC of S times 1 over SC plus R. Now I have VC of T sub 0 divided by S equals negative IC of S times 1 plus SRC divided by SC. So next I have negative VC of T sub 0 divided by S times SC divided by SRC plus 1 equals IC of S. And then I have negative VC of T sub 0 times C divided by SRC plus 1 equals IC of S. Putting this into standard form, I have negative VC of T sub 0 divided by R times 1 over S plus 1 over RC equals IC of S. And so now I have IC of S equals negative VC of T sub 0 divided by R times 1 over S plus 1 over RC. So IC of S is negative. So it means that it is opposite in direction to the schematic and is coming out of the positive terminal on the schematic. With the correction on the schematic, this becomes IC of S equals VC of T sub 0 divided by R times 1 over S plus 1 over RC. And so that translates into the time domain as IC of T equals VC of T sub 0 divided by R times e to the negative t divided by RC. So it comes out to be the same as before, so this checks out. The current plot. So the current plot is going to look like this. And just to note that the positive current on the plot indicates that the current probe direction orientation is correct. That's when you do this current plot in a simulator. Okay, so now using the other model. What about the other model? Well, the other model that uses a current source to model the initial condition can be used. The voltage source VC of T sub 0 divided by S is taken out, and a current source C VC of T sub 0 is used in parallel with the passive impedance element. So I'm going to go to my schematic, and I'm going to assign current directions. And see over here I have C VC of T sub 0, this current source. That is now the other type of model that we have. So note that VC is the whole assembly of the passive element plus the initial condition element. So voltage, current distribution at VC. So the current distribution at VC is IR of S plus C VC of T sub 0 equals VC of S minus 0 divided by 1 over SC. So now I have 0 minus VC of S divided by R plus C VC of T sub 0 equals S C VC of S. Next I have negative VC of S divided by R minus SC VC of S equals negative C VC of T sub 0. Then next I have VC of S divided by R plus SC VC of S equals C VC of T sub 0. VC of S times 1 over R plus SC equals C VC of T sub 0. Next, VC of S times 1 plus SRC divided by R equals C VC of T sub 0. Next I have VC of S equals RC VC of T sub 0 times 1 divided by SRC plus 1. And finally I have VC of S equals VC of T sub 0 times 1 over S plus 1 over RC. That translates into the time domain as VC of T equals VC of T sub 0 times e to the negative t divided by RC. That's the same as before, so this checks out. Voltage distribution equations. Well, can voltage distribution equations be used instead of current distribution equations? Yes, this is what I'll show you next. So, voltage distribution at the left mesh. 0 equals VR of S plus VC of S. This is according to the schematic. 0 equals IR of S times R plus VC of S, and that is going to be my equation number 1. Voltage distribution at the right mesh, VC of S is just simply equal to VC of S. Now remember that VC of S includes the whole assembly of the passive as well as the active element in the model. So it should not be decomposed into IC of S divided by SC equals VC of S. Equation 2 is redundant but cannot be decomposed any further when using the model. However, IR of S equals IC of S can. Okay, so we will have to take notice of the fact that at node VC of S, there's current distribution that we can put into equation 1 to have an expanded definition of IR of S. So I'm going to assign the current of the passive element of the capacitor model I1 of S and the current of the active element of the capacitor model I2 of S. According to the schematic, IR of S plus I2 of S equals I1 of S. So with this relationship of IR of S plus I2 of S equals I1 of S, I'm going to now decompose that and have IR of S plus C VC of T sub 0 equals VC of S divided by 1 over SC. And then I'm going to isolate IR of S and have IR of S equal SC VC of S minus C VC of T sub 0, which is also equal to IC of S according to the schematic. And that is our equation 3. So this is a current distribution equation that we will use in the voltage distribution equation. So going back to that voltage distribution equation, equation number 1, 0 equals IR of S times R plus VC of S. We are now going to put equation 3 into equation 1. Now that gives us 0 equals, in parentheses, SC VC of S minus C VC of T sub 0 times R plus VC of S. Okay, so now with this expression 0 equals SC VC of S minus C VC of T sub 0, all of that times R plus VC of S, then that now becomes 0 equals SRC VC of S minus RC VC of T sub 0 plus VC of S. And then now we have negative SRC VC of S minus VC of S equals negative RC VC of T sub 0. And then now we have SRC VC of S plus VC of S equals RC VC of T sub 0. And now we have VC of S times SRC plus 1 equals RC VC of T sub 0. And then finally we have VC of S equals RC VC of T sub 0 divided by SRC plus 1. That finally gives us, when we put this into standard form, we have VC of S equals VC of T sub 0 times 1 divided by S plus 1 over RC. And then that translates into the time domain as VC of T equals VC of T sub 0 times e to the negative t divided by RC. So that is the same as before, so this checks out. Now the current, deriving current from equation 3. IR of S equals S C VC of S minus C VC of T sub 0 equals IC of S. That's equation 3. And then I'm going to use the answer VC of S equals VC of T sub 0 times 1 over S plus 1 over RC to find IC of S. So I'm going to now reform VC of S into VC of S equals RC VC of T sub 0 times 1 over SRC plus 1. And so now I'm going to put the expression for VC of S into equation 3. And when I do that, now I end up with IC of S equals SC times RC VC of t sub 0 times 1 over SRC plus 1 minus C VC of t sub 0. And then now I have IC of S equals SRC squared VC of t sub 0 divided by SRC plus 1 minus C VC of t sub 0. And then now for IC of S, I'm going to have IC of S equals, combining these two terms, that becomes SRC squared VC of t sub 0 minus SRC squared VC of t sub 0 minus C VC of t sub 0 divided by SRC plus 1. And as you can see, these two terms here will cancel each other out. And then now we have IC of S equals negative C VC of t sub 0 divided by SRC plus 1. And so now IC of S is equal to negative VC of t sub 0 divided by R times 1 over S plus 1 over RC. So IC of S is negative, so it means that it is opposite in direction to the schematic and is coming out of the positive terminal on the schematic. With the correction on the schematic, this becomes IC of S equals VC of t sub 0 divided by R times 1 over S plus 1 over RC. And so now the time domain expression for IC of t is IC of t equals VC of t sub 0 divided by R times e to the negative t divided by RC. And now that is the same as before, so this checks out. Okay, so the power of the capacitor. Ideal capacitors do not dissipate power. If you ever have a capacitor that's getting warm or even hot, then that could be a safety hazard because it's not supposed to do that, and it could even explode on you. So it's not supposed to do that. Capacitors do not dissipate power. So when I talk about the power of a capacitor, I'm talking about this is what the capacitor handles. The time domain equation is PC of t equals VC of t times IC of t, which equals CVC of t times dVC of t dt. So I'm just going to be working in the time domain here with it. And so using the time domain expression in the equation for power, which is, what did we have? We had VC of t equals VC of t sub 0 times e to the negative t divided by RC. We are now going to have PC of t equals C, in parentheses, VC of t sub 0 times e to the negative t divided by RC times d VC of t sub 0 times e to the negative t divided by RC divided by dt. So next we have PC of t equals C VC of t sub 0 e to the negative t divided by RC, all of that times VC of t sub 0 times d dt of e to the negative t divided by RC. Next I have PC of t equals C VC of t sub 0 e to the negative t divided by RC times VC of t sub 0 e to the negative t divided by RC times d dt of negative t divided by RC. Next I have PC of t equals C VC of t sub 0 times e to the negative t divided by RC times VC of t sub 0 times e to the negative t divided by RC times negative 1 divided by RC. So now I have PC of t equals negative VC of t sub 0 squared divided by R times e to the negative 2t divided by RC. So note, the correct sign for power is already included in this derivation, and that's according to the passive sign convention. So power of capacitor, we can also get the same result for power by multiplying current by voltage. So you can take that approach to it as well. So PC of t equals VC of t times IC of t. VC of t equals VC of t sub 0 times e to the negative t divided by RC. IC is what we got before, is going to be IC of t equals VC of t sub 0 divided by R times e to the negative t divided by RC. And then when we multiply those two together, we get PC of t equals VC of t sub 0 times e to the negative t divided by RC times VC of t sub 0 divided by R times e to the negative t divided by RC. Moving on here, restating that again, it's VC of t sub 0 times e to the negative t divided by RC times VC of t sub 0 divided by R times e to the negative t divided by RC. And so since the current is leaving the positive terminal of the capacitor, the power is negative. So PC of t equals negative VC of t sub 0 squared divided by R times e to the negative 2t divided by RC. And so that is our final expression for PC of t. So we have to make sure that we include that negative sign there because current is leaving the positive terminal of the capacitor. Okay, so that makes the power negative. Same as before, so this checks out, okay, because remember that's what we got from before, so that checks out. And the power plot is going to look like this. So note, the negative power on the plot indicates that the capacitor is delivering power. Okay, so we're down here at negative 25 milliwatts, and then going on and on with time. And as you would expect, as it gets to the end of its time constant, then the capacitor has no more power. It has no more energy in it. So, of course, it can't deliver something that it doesn't have anymore. And so your power eventually gets to be 0. Now, the energy of the capacitor. So I start with PC of t equals dWc of t dt, which also equals VC of t IC of t. And so PC of t equals dWc of t dt, which equals VC of t C dVC of t divided by dt. So now, because that's your IC of t, IC of t is equivalent to this, right? Okay, so PC of t equals dWc of t dt equals C VC of t dVC of t dt. And so next we have PC of t dt equals dWc of t, which equals C VC of t dVc of t. And so now we have this, we're integrating PC of t with respect to time here, but we just set up our integrals initially, and we do that to these other terms over here, which is our dWc of t and our C VC of t dVc of t. We integrate on each one of these terms here. So next we set up our integration limits and continue to integrate. And then we carry on with our integration. We evaluate what's in the middle and what's on the right side, and then we get this. And then after that, we continue with our integration. The PC alpha, D alpha, that's a generalized statement there. So what's in the middle and what's on the right side, you can continue on. And so you have all of that equal to WC of t minus WC of t sub 0 equals C times VC of t squared divided by 2 minus VC of t sub 0 squared divided by 2. So what that all gives you is a summary of the energy with time. The sum energy of time is equal to WC of t minus WC of t sub 0 equals C over 2 times VC of t squared minus VC of t sub 0 squared. And that is my final energy equation there that I have. Okay, so now for the energy plot. So the energy plot is going to look like this. And note that since the power was negative, the energy is negative. This is a direct result of integration of a negative area on the power plot. Negative energy on the plot means that the capacitor delivered energy. This plot shows the sum of energy that has been delivered over time. So, of course, this is in units of joules. And so at 0 seconds here, okay, so this is plotted over time still. That's my 50 milliseconds, my 5 time constants. And so at 0, how many joules of energy has it delivered? Well, 0. By the time I get to about 10 milliseconds, how many joules of energy has it delivered? When I say it, I'm talking about the capacitor. So how many joules of energy did the capacitor deliver? Well, it gave over 100 microjoules of energy to it. Then when it's at 20 milliseconds, how many joules did it deliver to the circuit? A little bit over 120 microjoules, and so forth and so forth and so on. And so it's looking like, I'm just going to give a visual estimate, it looks like about 125 microjoules that it gave in total. So this is basically, the expenditure of energy over time, and it's telling you how much at what time, and that's the correct way to interpret this energy plot. That is all that I have on these slides, and that's basically it. That covers everything that I wanted to get to in this lecture presentation here. Thank you for watching. Hopefully it was helpful for you, and have a nice day.